All right, as people funnel in, I'll go ahead and introduce the session. My name is Jen Kaiser. I'm an assistant professor at Georgia Tech, stepping in for HAQAST member Ted Russell, also at Georgia Tech. So we'll be talking about models and observations, the strengths and limitations of satellite data with our speakers listed up here, and I'll let them introduce themselves to save some time. So our first speaker is Betsy Farris from Ball Space Engineering, or Ball Aerospace. If we could hold all questions to the end for our discussion, that would be great. And I'll hold up the chat.
All right, thank you, everybody. I'm Betsy Farris. As she said, I'm with Ball Aerospace. Really excited to be here. Been attending HAQAST remotely. It's my first time in person. It's an awesome community. So yeah, I'm a payload systems engineer. I'm actually also standing in for someone, but I took some liberties and inserted some slides that I think are interesting. As a payload systems engineer, I work on the sensor side of the technology used in these satellites to measure air quality. And as a systems engineer, that means I work a little bit on everything, which means I'm not an expert in anything. So I'm going to use that as an excuse for anything difficult. But I can always connect you if you have other questions about the technology to our experts. So I wanted to introduce really kind of the history of Ball Aerospace with air quality measurements, giving some perspective of how we end up working on these air quality missions. So this example is really related to GEMS and TEMPO, and looking forward to the next generation of air quality satellites. So we have funding from all sorts of different places, as you can see in the bottom right. But the NASA Earth Science Technology Office, that provides a lot of the smaller grants for some of our research and development. So this could be anything from components to airborne systems. Like to give a shout out to GeoTazo. So there's lots of airborne instruments that are still being used today to do the higher resolution studies. And then, we move on from R&D to sort of these NASA missions such as TEMPO. And we collaborate directly with scientists to, win these opportunities to build the instruments to provide the data for the scientists. So I'll talk about it again, but looking forward, the next generation, Ball has won a few phase A studies. So that's kind of looking at the initial architecture for future NOAA satellites. So this is really a success story from the Ball perspective, taking research to operations. So I know some people in this room are very familiar with this image, but just for context, Ball has built 2 of the 3 instruments that are listed here. Sentinel-4 hasn't launched yet, but we are definitely uniquely positioned to build and work with people to create these measurements for air quality. While this is a very exciting image, of course, I think we've heard about it a lot today. It's also a little jarring, as you see how much of the globe does not have these measurements. And I also like to give this as sort of an introduction to the geostationary satellite measurements. So let's see, actually, I'm gonna go on the next slide. So I'm not gonna try to do any GEMS science here with this slide, but it is of note that one of the more exciting things about geostationary satellites are the ability to have these hourly measurements. So geostationary means it really just stays over the same part of the globe. And because of that, excuse me, we're able to do really unique measurements. So this is 2 different data products from the same day, and you can see different hourly measurements. So it's definitely very exciting and unique compared to other instruments. So this is sort of the slide that I snuck into this talk because I'm an instrument person and I love explaining how the instruments work. In case people do not know how GEMS and TEMPO work, we talk about those hourly measurements. Really the key to these 2 instruments, which are very similar, is this step-stair mechanism. So there is a mirror inside of both of these instruments that does the actuation that scans over the field of regard. So you can see the rectangle for both of those areas over North America and parts of Asia. And step stair is kind of obvious what it means. The mirror in both of these instruments moves from one location and then it stares, collects images, as you can see those. They're then co-added, so you can think more images, more signal to noise. And then it creates, with lots of processing, eventually the data products that people here are very familiar with. The reason I wanted to bring this up and maybe open up a can of worms if people have questions, from an instrument perspective, there's all sorts of requirements that are balanced when designing an instrument. So you can think about, if you stare for a really long time, you can build up that signal. You can get a lot of information, but if you're staring in one area for a really long time, you're going to have some trouble revisiting the entire field of regard in 1 hour. So this is something that I think is just interesting to throw out there, but also you can think about the step stare as opening up all sorts of opportunities for special studies, which I'm sure some of the tempo folks will talk about. Also want to just show what the inside of these instruments look like. Every instrument's a little bit different, but this just shows the light path through the instrument, hitting that scan mechanism, and then there's a spectrometer. So that's what splits up the light into the different wavelengths that's used for the science. And then another subsystem that I like to mention, but again, not an expert in, is the calibration mechanism. So I've heard a lot of talks where people ask about calibration, especially the low-cost sensors. It's a different game with satellites, but we have, for this architecture, essentially something, the diffuser that we look through to give us a known scene. So this is the very basic way of how calibration works, but we can talk about it more if you have questions. So just thinking about, what's next for Ball. I already mentioned we were lucky enough to win several Phase A studies for the GeoXO constellation. I primarily have worked the atmospheric composition study, and that's a very similar architecture to the tempo instrument. So another thing we like to mention is looking at the launch dates for when tempo is launched and when ACX is estimated to launch. You can see there's about a 13-year difference. And this is a bit of a concern, I think, from a user perspective. We have spatial gaps. We also have temporal gaps in these critical data that we need for the community. So again, we think we're uniquely positioned, having built 2 of the 3 geostationary air quality instruments. We also have spares for from GEMS and tempo builds. So we do think that it would be efficient to use some of these parts to build possibly either a continuity instrument or something to fill in one of these gaps. So of course, there's always the question of funding. I think funding and money is a big challenge for making these types of measurements happen. But just something to note, giving a shout out to Aaron and the early adopters. This community is so ready to go for these data. We don't want any gaps for these critical measurements. So with that, I like to mention, well, one, just I've worked on methane sat. I think methane is also a very interesting topic, a little outside of today's conversation, but Ball has done that traditional R&D through NASA, going to NOAA pathway. But I think in today's aerospace and instrument world, there's non-traditional ways to get the measurements you need. And this has been a really cool success story for Ball, working with now Methane Sat LLC and Environmental Defense Fund to work on the Methane Sat instrument for their particular science. So I like to give a shout out to that team and that instrument and those users as well. And so I think the Methane Sat's very much in the throes of testing right now, and I think the plan is to launch next year. So with that, I think, going back to this image, it's definitely an opportunity, and really there's some criticality in thinking about providing measurements for the rest of the globe. There's some folks at Ball. I can connect you if you're interested. Sheldon, who was supposed to talk, he's out and about trying to really look for alternative ways to provide data for these areas. So, it might not be the traditional NASA NOAA type measurement. Maybe it will be. Tell your congressperson. But I think it's going to take some collaboration to be able to get these measurements, and we're hoping to be a part, or at least help enable by spreading the word about how critical it is to create these measurements. And so that's all for me, and I'm just happy to be here.
All right, thank you, Betsy. Our next speaker is Brad Pierce from the University of Wisconsin-Madison.
Thanks. Okay, I'm not going to talk about tempo. I'm going to talk about polar orbiting data, and I'm going to talk about it from a perspective of a modeler mostly instead of a satellite person. So again, comparing models to observations. So a little background, it's great to hear that 30% of the audience hasn't been here before. And so I'm glad I put this slide in just so that we're all on the same page. I'm going to talk about Earth observations from polar orbiting satellites. This schematic in the upper right, these polar orbiters they orbit in a single orbit around the Earth. The Earth moves underneath them. And as a result, they're able to sample the full planet twice a day, once in the daytime, once in the nighttime, which means that you're really only getting one observation over a particular place, particularly in the daytime when we're doing most of the composition retrievals. So it's good that it can see the whole planet. We just saw the talk from Ball saying there's the geostationary, particularly for these multispectral retrievals, are limited to certain geographic regions. And then also when they're making these measurements, there's typically a swath. It's measuring across a swath, and it's measuring typically in a sun synchronous orbit, which means that it sees the same point in the planet at the same time each day. So Tracy showed this slide earlier. I'm going to focus on the NASA Aura and HAQAST satellites. It's part of the A train, the afternoon constellation. Aura is the one circled down in the bottom coming across, and HAQAST was the one at the top of the orbit. I'm going to focus on OMI, MLS, and AIRS measurements for the most part. To start out with, I'd like to talk about the Aura, OMI, MLS, tropospheric ozone column. Lots of acronyms that I will be defining. Aura has something called the microwave limb sounder, MLS, which measures profiles of stratospheric ozone among other species. The Aura ozone mapping instrument, OMI, measures total column ozone in addition to other species. If we take the difference between that stratospheric column or the total column and the stratospheric, we have a residual. It's the tropospheric ozone residual. It's about 10% of the total column. So we're looking at small differences between large numbers. What we get though with this Aura OMI minus MLS TOR, tropospheric ozone residual, is the long-term record of these tropospheric ozone columns, which are great for evaluating against models. In this case, I'm showing comparisons between a 10-year chemical reanalysis that we did using our RACMS model and a simulation of OMI and MLS data with this OMI minus MLS TOR. Top figure is the model, bottom figure is the retrieval. And you can see clearly that the model is higher than the OMI minus MLS TOR. It's higher consistently by about 4 Dobson units, which is about 15% of that tropospheric column. So that tells us something using these measurements about our biases potentially in our model. However, if we look more carefully at the OMI retrieval itself, it's a UV retrieval, and it has lots of sensitivity in the stratosphere and less sensitivity in the troposphere. The way that we get at this is, in this case, we're looking at the radiance contribution functions at different wavelengths. This is the figure in the upper right. And what you can see is there's quite a bit of information above 10 millibars in the stratosphere and less information below 100 millibars in the troposphere. And in particular, you can see that it kind of peaks somewhere in the mid-troposphere and not much information at the surface. We really need to be accounting for these kind of sensitivities in our comparisons between satellite measurements and models. Because the OMI minus MLS TOR is a monthly product, we can't account for any of these sensitivities of the measurement to the inner comparison. And this just shows an example of where we see large differences. The top panel is our ORA reanalysis for May 2016, and the bottom is the OMI minus MLS TOR. And you can see that we're clearly much higher than what is in the TOR. So let's look into that in a little bit more detail. Whoops. Okay, so now I'm going to look at another satellite product. This is something called MUSES, which is an acronym for basically a multispectral retrieval. They're using information both from AIRS, which is the atmospheric infrared sounder, and OMI. And so they're using information in the thermal infrared and in the UV to do retrievals. And this figure on the bottom, I'm not going to go into lots of details on it. Don't worry about the test part. But if we look at AIRS plus OMI, again, these are average kernels. They're like how much information is available at a particular level. You can see AIRS plus OMI has more higher averaging kernels in the troposphere than either AIRS by itself or OMI by itself. So we can use this combined multispectral retrieval to get more information about tropospheric ozone. And in particular, we can account for the satellite retrieval sensitivity explicitly in our comparison with the model. And that's what we're doing here. So this is now for April, May, June of 2016, just like we were looking at May before. And on the upper left panel, you can see that in terms of a mean profile, our Rackham's ORA reanalysis is in extremely good agreement with this MUSES retrieval. In fact, our mean biases are less than 5%. So by accounting for the detailed information content of the retrievals, we're able to show that, in fact, our assimilation of OMI MLS has resulted in a chemical ozone reanalysis that's very consistent with a retrieved AIRS plus OMI retrieval. And the key here is that by using it at the level 2 swath level, we're able to do these comparisons and account for the sensitivity of the retrieval. So I'm getting close to the end. In terms of other sensors, here's a comparison between tropo-OMI column CO and in this case, a new modeling system that we have, which is the operational UFS model from NOAA with Rackham's chemistry in it. This is a control experiment for the 22nd of July in 2019. And you can see in this panel, the large hot spot in CO is over Siberia. And you can see large enhancements of CO associated with Siberian wildfires. If you look at the panel on the right, that's when we look at our model, mapped to the level 2 swath and applying the tropospheric, the tropo-OMI CO column averaging kernel. And here's what we get if we don't apply it. And you can see, again, there's significant differences. If you don't account for these differences, you're going to have a poor representation of the biases in your model. The final thing I want to talk about is the need, again, to map to the level 2 swath data. This is a figure now on the same day. This is Veer's aerosol optical depth. You can still see the enhancements in aerosol optical depth over Siberia. And this is the model output every 6 hours, showing the sort of transport of these smoke plumes and the changes in emissions associated with smoke plumes that need to be captured. That variability on a daily scale needs to be captured to do a direct comparison with these measurements. So again, it's very important to look at the data from a swath perspective to capture pollution transport. So lots of technical detail, way too complicated for most of the people in this room. Do I really need to do this? Where do I get the data? Where will I get the tools to do these comparisons? And that's my last slide. Melody's Monet is being developed now by NCAR and by NOAA at the Chemical Sciences Laboratory and Global Systems Laboratory. And this is a package, a Python package that will be publicly available that will do all this for you. It will account for all the information about the averaging kernels. It'll account for the various different acquiring the satellite data, having input from different models in a very modular way. This is under development right now. Louisa Emmons at NCAR is the lead of this effort. And first of all, I suggest starting to take a look at that. It's pretty mature for surface. Its aircraft comparisons are being developed. and satellite data is also being developed. And they're reaching out to people in the community to help support this. So with that, I will close.
Fantastic. Thank you, Brad. Our next speaker is June Wang from the University of Iowa.
Well, good afternoon. I really thanks the meeting organizer to give me the opportunity to speak. And I also like to thank my group of students, Manzo, Megan, Kristen, Loranda, Cassia from University of Iowa, as well as the NASA GML team, Navy Research Lab, NAPS team, and many stakeholders like Zach in the audience who participated in the FireAQ weekly briefings this past summer. I'm by training using atmosphere science, and I'm working in the College of Engineering, try to do a little bit more applied science here. So let's go here. So the topic of the session is about models and satellite observations. So let's, I just want to start with a case study to illustrate some of the model limitations and the strengths of satellite observations. So what I'm showing here is actually the real slides that we provide in the weekly briefing for the winds for August 16th. What you can see here is that in the north central part of the Canada, there is a very deep trough, and that leads to a lot of precipitation near the border with the U.S. And when you look at the air quality, you can find over that region, the air quality is very clean. However, when you down the bottom, you see all the model predictions from GSFP, GLCF, NAPS model, and including the ensemble, we basically take the average of 3 models. You can clearly see over there, we see very 6 smoke plumes. Obviously, all the models are wrong at this point because there are precipitation. There shouldn't be a lot of smoke. On the other hand, you also see over the northwest US, in Oregon and the Washington area, the prediction actually did a pretty reasonable job there. So anyhow, we're going to have a deep dive into here. So this is showing the world view. Again, is also the NASA's assets. On top of it, I'm showing the GPM precipitation data on that day. You can clearly see that thick cloud is associated with precipitation. So if the model is not able to capture or predict the precipitation very well, chances are the model simulation for the smoke transport will be hugely incorrect. So that's one point here is that the other models are wrong, and some of them in some places are useful. And I'm going to look into a bit more about what we think is probably useful is in the northwest of the U.S. And you can see I highlighted there is a Montana, the state of Montana. What you see there is that their air now shows the lots of the unhealthy air quality conditions. But on the northwest, further northwest, there are a lot of the unhealthy air conditions as well. But when you look at the down in the bottom, you see the VIIRS true color image. You see that actually the smoke is very dense over there in Montana. But the air quality from the EPS monitoring side shows actually they're moderate. Actually, many places in the state of Montana is actually very healthy. So you wonder why there are smoke over there, why the air quality is actually pretty good. So this is our own product. What I'm showing here, let's focus on first of all, let's focus on the top right. That's our own retrieval of a troposphere Earth optic depth. You can see the optic depth there is go up to 3, very, very thick, dense plume. There's no question there are smoke there. However, on the lower left, what I'm showing here is our own retrieval of the aerosol layer height. I call it the aerosol optical center height. That tells you how high the smoke plume is. What you see is that in the circles in the red, the smoke plumes are generally below the 3 kilometers. That is also showing corresponding very well to the air quality now, shows where the air quality is in unhealthy condition. However, when you look at my red arrow bar there, that's where the smoke gets transported to Montana. You can see the smoke plume now goes up to about 7 kilometers. That's where you can see the air quality there actually is moderate, and then actually in many places actually in very healthy condition. So this is kind of a new solid data that tells you where vertical the smoke layer is located, and we can mapping them. And this is what my second point is when you talk about satellite observations, that the new satellite observations will lead the way to tell you where the deficiencies of the model are, and give you more insight to interpret your observations from either surface observations or from your model, from the other observations that you have. So my 3 points here is that I talked to 2 points here. One is that our models are wrong. Some of them are useful at some times and some places. Observations, especially new observations, this is a way for improving models. This slogan is not from me, it's from one of the years in the MS meeting, says observation leads the way. So I have showed you the Air's optical signal height that can tell you where the smoke is located in the sky and how much impact they may have on the surface air quality. So I also want to say that the observations have limitations. First of all, observations only tell you what has happened. They will not tell you what happened tomorrow. Second of all, you can apply data simulation or AI or machine learning. Those are all not trivial tasks. It's a very heavy technical endeavor to get to the surface air quality data. But the applications really requires a timely alert or advisory of air quality on health, right? We can also talk about how the air quality affects the human health in terms of the effective life lost. This is all good. We will continue to push that limit. So hopefully we'll have more regulations on the emissions and cope with the fires or not. But day to day on the ground, you want to know what happened tomorrow in terms of air quality. And should our kids go outside to play soccer? That's a very practical question. I have 3 kids. in this summer, we have multiple times that our community has to cancel their practice of the soccer event because their smoke goes come to the Midwest. So how am I doing with time? Oh, I still have some time. Okay. So I'm going to talk a little bit more about another new data set, which I kind of alluded to, called the fire combustion efficiency. So one of the things is that the fire, in order for fire to happen, there need to have 3 elements: oxygen, heat, and fuel. Without oxygen, fire will not occur. Currently, the solar observation can give you the heat and the fuel. You can map the surface type, estimate how much fuel it is. You can map the fire radical power, tell you how much heat it is. However, you don't know how the oxygen play a role in the combustion efficiency. With oxygen, we know it cannot have fire. So we try to get more data about to what degree the combustion is complete. You know, for the most time, for the biomass burning, if you have fires, most of them is made of carbon that goes to CO2. But if incomplete combustion, they go to carbon monoxide. So we have been developing a product called the visible energy fraction product, which I'm not going to go into details here. What I'm showing you here is that on the top row is our new product called visible energy fraction. That tells you which part the flaming is, because the flaming by definition need to have visible light. So on the bottom row is the FRP that normally you will get from NASA. I want to draw your attention to the central column, where you see, and including the on the right, the third column as well. What you see here is that the FRP is always very high within the parameter of the fire, where our VF shows actually at the parameter of the fire. At the edge of the fire, the VF is much higher because that's where the flaming should be. So this tells you that you can use this data to actually predict when the fire lines, to locate where the fire lines are and predict the movement of the fires. So you wonder why FRP within the fire parameter is so high. Well, here is hopefully is the video that I can play here. So what you're showing here is that when the fire line progress, you see what left behind is all that white is smoke plumes. Those plumes are actually generated by smoldering fires. But because they are left over, so when the fire progresses, the ground is heated up. So in terms of area, you know, the heat that generated by that sweeping of the ground by the fire line, that heat is actually very, very high. But those are the areas that are not necessarily indicated the fire lines. So with our product, we can look at the fire lines and I can tell you where the combustion is more complete. In other words, there are more CO2 than CO. There are less white smoke particles than the white smoke particles behind the line of the behind the flaming lines. You can see this movie again. You can clearly see that the fire line is actually associated with less amount of the white smoke particles because those are more complete combustion. Most of them goes to CO2. I probably have 1 minute left, so I will just tell you that we actually validated this product with the EPS monitoring of NO2 versus CO. It's happening in California. There is 3 sites downwind of the fire, and you can look down on the days. Our characterized the modified combustion efficiency versus the CO2 versus CO. There are very good correlations there. So this product is now in pipeline for production, and maybe in I would say in a month or so, you should be able to get this data from NASA's website. So I have some other things to show. I think in time on each time, I'm going to skip that. So let's just move to the next one. Oh, sorry, is it all done?
Thank you, June. Our next talk is from a HAQAST ambassador, Amirhosein from Waste Management.
Try that. Yes. Okay. Good afternoon, everyone. I guess I need to clarify one confusion here, and that is I recently joined Google Research, and this is going to be a project of our collaboration with Waste Management. However, it would be great to first talk about a little bit of the focus of Google Research and what that does. So in the Google company, there is a section named Research that focuses on different innovative initiatives. One of them is the climate and sustainability, which focuses on 3 main topics: mitigation, adaptation, and resilience, and some platforms that are usually based on some advanced statistical, usually atmospheric or climate models that would help the stakeholders to try and basically achieve their sustainability goals. Now, one of the projects that could potentially ring a bell out of the mitigation or the adaptation of resilience is the eco-friendly routes that you've been seeing on the Google map when you're trying to go from A to B in a city, or from in the flights, for example, when you're trying to book a flight, it gives you an option of eco-friendliness and saving in the gas and the pollution. Now, this aim or this project is one part of those topics. It's part of the GHG reporting and accounting efforts of some of our stakeholders, being landfill owners and landfill operators. Waste Management is one of the biggest operators of landfills in the United States, with over 260 landfills across the United States. And as some of you might know, landfills are a major source of methane in the whole ecosystem of emissions from GHG emissions. Now, I serve a senior data scientist role in the Google Research, and this is going to be kind of an intro of what the project is, what type of problem we are trying to solve, and how we could get some help from the community of HAQAST. So the objective of this project is to, the objective of this project is to quantify the landfill emissions accurately. And by accurately, we mean with the lowest uncertainty possible. Right now, the methodology is to quantify methane emissions in terms of the emission rate is related to the oil and gas refinery projects. There are point sources, there is a flare, and it's much easier. It's much less complicated to correspond a ground-based concentration to a flare emission rate, or vice versa, through different models such as Gaussian models or so on and so forth. Where here, the objective is reporting, and that needs to be fairly accurate because there's some business justifications followed by, and there's some economic justifications that really matters. Now, it needs some high resolution, either emission rate or methane concentration profile, either on the ground-based level with the sensor measurements or audits from agencies, or satellite measurements from the column, atmospheric. And of course, there is a data limitation for each of these data sources, whether that's a ground-based level. Some of them give you concentrations, whereas the objective of this project is emission rate. And it's really hard to translate the concentrations on the ground level for specifically landfills, because they're not point sources, and usually they're a translation of a area source. So the figures that I've put on here are the 3 different data sources that are usually being used on when you're having an air quality problem, let's say. My background is from air quality. So when you have an air quality fusion, you have usually multiple sources of data set that each of them has some problem. For example, the ground-based data that we have there, this is the sensor grid that you see, different boundaries, different components of that landfill on the right top. The red sensors are showing the sensor that has the alert system going on, meaning that over a period of time, they have passed the threshold. Now, what that threshold should be and how that being translated to an emission rate, those are question marks. Now, satellite observation, that shows a GHG sat scan of a day that we had a detect day. By detect day, we mean the satellite has passed a certain threshold and could show us an emission rate of, let's say, 500 kilograms per hour or 600 kilograms per hour, but with a very high uncertainty. And that's always associated with the satellite data, especially with the methane. Now, we also have some airplane or drone scans that happens less frequently, of course, because they're not automated like the GHG, like the satellite or the ground-based, but they're also fairly accurate. The other problem with them, they're dependent on the height that they're measuring. Sometimes they're going off of the plume, they're not on the plume layer. So basically there are different limitations with each of these data sources that we are trying to come up with a statistical model / predictive model so that we could potentially solve the problem to the extent possible. That's always a good statement to make. Yeah. So the current state is how the waste management companies are trying to report their GHG emissions. Now, there are some mandates from regulations or from the agency to provide annual emission rates for each of the landfills. Now, when you're looking at each of the data sources, satellite data, which is the GHG sat, carbon mapper, emit, a lot of tools or data sets of satellite. From ground-based, you have concentration levels, which are not translated to the emission rate. Again, the objective here is the emission rate. Drones are usually not reporting the emission rates, and the modeling, which are currently not being on a level to be reported because the accuracy of these models being used for landfills are really low. Now, the only thing to report right now is the the satellite data points, which are potentially giving us a uncertainty level of 50 to 60% for emission rate. Now, that's a very high uncertainty when it comes to especially high numbers, because let's say that you have like a 2,000 kilogram per hour annual emission rate for a landfill. Now, 50% uncertainty, you're talking about 1,000 to, I don't know, 3,000. So that's a very wide range, and it's needs to be narrowed down so that we could actually do something about it. Because when you don't know information about something, you cannot do anything about it. So currently, the efforts are on the Google side is to try and see if we can fuse these 3 data sources and find a reliable predictive model based on the historical data of satellite, ground-based measurement, and of course, they frequently happen like established methodologies like drone and airplanes to find the best accounting and reporting tools. As I mentioned, there are limitations because this is not a point source and this is an area source. So there's a lot of partnership and there's a lot of information that will be useful on that side. If there's been any model that's been already implemented on the landfill side to be able to find an emission rate for an area source. Accuracy of the data or the model is really important here because we are trying to account for those. So take action on those data. It's the air column data. Which one we need to do? Should we translate the concentration from the ground-based to an emission rate on a breathable height, or should it be the atmospheric emission rate? These are the questions to answer. And of course, there is no, I would say, validated or verified model to come from a concentration to emission rate. That's a work in progress from our team to be able to put some concentration on the ground level and give some different sources on the emission rate level. Of course, the goals here are some early products that could be created by Google's research side for the waste management communities on alarm systems for emission thresholds, so that could automatically give the the field operators. That's kind of a mitigation part. And then sustainable emission reporting systems, that's going to be the platform that we're trying to develop, and that's going to be helpful on the economy side for these operators and for these companies, but also on the GHG reporting and kind of accounting, holding responsibilities, let's say. And of course, the other ultimate goal, which is a little far away right now, is the high spatial temporal resolution of low uncertainty data. That's very, very idealistic, but that's the ultimate goal. But we need to be passionate about those. I guess I have some time. Not actually. Okay, so that was good. Good, cool. So I guess on the panel, I would really welcome any questions, any information that we would have, because we are here to collaborate. Thank you.
All right, and we'll wrap it up with our last speaker, Aaron Naeger from NASA.
All right, well, all good. Yep. Okay, all right, thank you, Jenny. And thanks for inviting me here for talking on Tempo. I'm Aaron Naeger. I'm the mission applications lead of Tempo. This is a huge team. Who is familiar with Tempo in this crowd? Raise your hand. Who knows about Tempo? Almost everybody, okay. Let's see, definitely familiar faces, but people who I don't recognize too, which is great. So I will, initially when I came here, I was going to jump right into our first light data and some of our commissioning phase data. But with the really wide range of participants, I kind of want to do a briefing on Tempo. Betsy did a great job at kind of introducing the geostationary constellation and all that. So I'm not going to dig into that. Again, you've been I guess, introduced on that. Now, one thing that I do want to note, we have this great geostationary constellation. You know, we launched our Korean partners launched GEMS over Asia in February 2020. We launched Tempo just this past April. Now we're staring down at North America. And one key difference between Tempo and GEMS, even though we're very similar, is that Tempo operates on 2 different detectors. So we measure solar backscattered radiances from 290 to 740 nanometers. That will enable a really nice ozone profile product from Tempo. GEMS operates with 1 detector from about 300 to 500 nanometers. So they don't have that same kind of ozone profile information that GEMS is great, but we'll have an enhanced ozone product from Tempo for that reason with our 2 detector operation we have ongoing. So here's kind of our mission phase operational timeline. Actually, we started our nominal operations today. This is great. Cheer. Yeah. So we powered on. We launched April 7th. Beautiful evening, 12:30 in the morning launch window. It was a great launch. We powered on June 7th. We just ended our commissioning phase yesterday. I'll show some of that data here today. And our nominal operations are starting today. And that will extend through May of 2025. Again, that's our baseline mission length. We have a potential to be up there 10 plus years, depending on our senior review extensions in the future. So we have that capability there. Again, but even though we have a 10-year lifetime, that gap between what we'll have with Tempo and GeoXO down the road is still a threat, right? I mean, we need to fill that gap yet. And I do want to note that we have our our data is not public yet. I'll show some images today, but we have our level 2 and level 3 products, which I'll show here in a minute, planned for release in April 2024. And we'll have that, our offline products, extending back to the start of the commissioning phase when we do that, when we have it available. So we'll have data dating back to August of 2023 when we make it public in April, hopefully. And then we have near real-time products on the plate too. So those, our initial planned release of our near real-time products are going to be in January 2025. All right. So I want to just show, for those who aren't familiar, really briefly here, our list of level 2 products on the plate for Tempo. These are our baseline products, and we have near real-time products that are noted on there as well. We're hoping to get about a 2-hour latency with those near real-time products. So that's kind of the delay or the time lag between when Tempo makes its observation and when that data becomes public. Hopefully we'll have about a 2-hour delay there, time lag between that operation. So I kind of show some key variables here. We have our ozone profile, which I mentioned earlier. And within that profile product, we have tropospheric ozone information and our 0 to 2 kilometer ozone information. So we have an ozone profile information in that. That would be at slightly coarser resolution noted on that slide compared to our nominal footprint size of Tempo of 2 by 4.75 kilometers squared. We have to do a little bit more co-adding of pixels to make that profile product of precision required for Tempo. So that's why we see that 8 by 4.75 kilometers squared resolution planned for ozone profile. Our other products like NO2, formaldehyde, those are at the Tempo nominal footprint size. Our NO2 product will be of high precision and accuracy. We know that. We have really great NO2 data from Tempo. And we have our aerosol products as well with UV and visible AOD, and level 3 products on the table for Tempo. So those are the same information content essentially as our level 2 products, but at a gridded format across the Tempo field of regard. And even our offline products, our baseline will have pretty low latency. So we're talking about 3 to 6 hours, even for those baseline products listed on that table. And I do want to note one thing. We talk about limitations of satellite data, right? To convert this data, or solar backscattered radiance level 1 data, to our level 2 products here, it takes a priori information into a retrieval algorithm to make these level 2 products available to the user community. Our a priori information being input into our algorithms, or GOCF, that's model input information, which leads to uncertainties in our satellite data, right? So, and there's been papers published on this, 25% like uncertainties that can be tied back to this a priori information that we have as input into our retrieval algorithms. Again, all hourly, daytime hourly, and we even have sub-hourly information for Tempo. We have additional products as well. Here they are. Don't go too much into those. You can read through them. Sulfur dioxide is one of those. We have a Tempo GOES-R synergistic product on the plate too for Tempo with an enhanced aerosol product, and those same level 3 versions of those products on that table as well. I want to just briefly note that we are developing a lot of tools, distributing for Tempo in preparation for Tempo. Our Atmospheric Science Data Center, we have folks here in the crowd who are a part of that team. They are working on a lot of these tools that are being developed for Tempo. We'll have Tempo in our Earth Data Search portal. We have some of our pre-launch proxy data there right now for early adopters to download and take a look at. We have Tempo imagery and worldview. Our EPA partners built a great RSIG gateway that will serve up Tempo data as well. And we'll have ArcGIS capabilities being built for the mission too. Just briefly on the footprint size, we have high temporal resolution, daytime, hourly, and sub-hourly, in addition to high spatial resolution. So there you go. Pick your favorite location across the Tempo field of regard, and you can kind of see the Tempo footprint size over that location. Really high spatial resolution across the US in general. We lose a little bit of that over Canada, just due to the fact that we are geostationary, and we have a little bit coarser resolution spatially in the far north parts of our field of regard. And kind of zooming in on the LA basin here, I was kind of overlaid Tempo footprints there and showing kind of the Tempo, kind of suburban resolution you'll get for Tempo. And I'm running out of time, So instead of showing this right here, I'm gonna jump right into our first light data. I do want to note our tropospheric ozone. This is showing I won't show much ozone first light data. So this is our pre-launch data, our 0 to 2 kilometer ozone, tropospheric ozone, just showing the capability of Tempo to be sensitive to ozone and show ozone profile information and track ozone throughout the troposphere and fills gaps in the surface monitor coverage as well. So I'm going to jump right into our first light. John Haynes showed this earlier. I won't really go. I'll just show it again because it's beautiful data to look at. This was our first light on August 2nd. We performed 6 daytime hourly scans across our Tempo field of regard on that day. And you'll kind of see we're looking at the whole field of regard. We'll zoom in on the northeast corridor here in a minute and look at the high NO2 emissions from the traffic corridors. There's other features on here too, which I will highlight here in a second, that are being shown over those big metro urban areas. A lot of information we're seeing here and capturing with Tempo that we have not yet seen to date with our low Earth orbiting data. And now looking over Texas here, in the major metro areas of Houston, Dallas, and the high NO2 emissions and pollution from those regions, and then now over to California and kind of zooming in on that region as well. Okay, so I do want to note, kind of show some individual static images of NO2 tropospheric columns from the data here. This is zooming in on this northeast area here. And it was one Friday evening. I remember I was invited out for dinner. I'm like, I can't go to dinner. I have to look at the Tempo first light data all night. This is what I did. So I'm kind of picking out features here, what we're seeing here. We have coal plants actually that we're seeing some NO2 emissions from. That I-95 corridor there is being highlighted. You can kind of see the major difference between that 12:14 p.m. Time frame compared to 4:24 in the afternoon there. So we're seeing a lot of variability there diurnally with those NO2, with that NO2 pollution. Same kind of thing here over Texas, right? We have the I-35 corridor there. Some NO2 tropospheric column enhancements in that area. There was actually a small scale fire that was I'm highlighting up there that day as well, which Tempo captured, and coal plant production as well. I'm sure our TCEQ, Doug Boyer, knows this area very well and can probably pick out features on there too of where we're seeing NO2 pollution from. And here zooming in on California, same kind of thing. We have our major traffic corridors. There's a lot of things happening there in that Central Valley, right? Not only traffic emissions, but there's likely ag pollution there from NO2. We have a bunch of industrial areas around there. There's a fire breaking out on this day, which I highlighted there in the earlier morning hours, actually. And then we have more areas of just enhanced NO2 pollution from our major urban areas. And John Haynes mentioned the Mexicali area here, which is sticking out very well in the data. And there's actually an article there showing the major air pollution issues from factories in that region. And we're seeing it from Tempo now. And I'm probably out of time already, but give me another minute or so I can kind of go through the total ozone. This is brand new data that we're looking at. To the left, we have Tempo hourly total ozone information. To the right is OMPS, our low Earth orbiting data. And now we're seeing this daytime diurnal hourly evolution of total ozone over the Tempo field of regard for the first time. More commissioning phase data here. This is hourly, zooming in. Again, tropospheric NO2 columns from Tempo. This is from October 6th during our commissioning phase pretty recently. I'm just looking at the diurnal daytime evolution, again, of NO2 over this US West area. And there's a fire actually breaking out too on that day in that northern Arizona area, in addition to all those major urban areas where the NO2 pollution is peaking. Here's Tropomi for that same day. So we're really excited about what we're seeing with Tropomi and Tempo right now. Pretty good comparison qualitatively. And our validation team is working on improving our algorithms and getting that data ready for the public release in April 2024. Again, kind of just showing the October 6th use case here. Fire on our Modus Aqua True Color is picking out in that NO2 that NO2 column enhancement there from that fire smoke event is definitely being picked up by tempo on this day. This was not observed by Tropomi. And this is October 8th, 2023. Zooming in on Texas here and looking at the, let me play that video. Again, same thing, this hourly NO2 daytime information. I'm sure there's some of our oil and gas activities there in the basin, picking up on that NO2 enhancement. The major metro areas, the traffic corridors, a lot of stuff is happening in this region here. And I'm sure folks in the audience who are more familiar even know more than I know right now in terms of the NO2 pollution source emissions in this region. Tropomi tempo, a comparison on that day, October 8th. Again, very excited about the good comparison we have here with Tropomi compared to our brand new tempo data. This is provisional, right? This is not even validated data, but we're seeing already a good comparison between Tropomi and tempo. And I'll kind of end here. I'm talking too much. But here's a zoom in to Chicago, brand new data here too, looking at Tropomi versus our hourly daytime NO2 data from tempo. And again, right when we had that comparison at 12:20 approximately in the afternoon, there you can see that both Tropomi and tempo pick up on this major NO2 enhancement from the major Chicago metro area. Beautiful. Here we go. My thoughts on what tempo can do, provide. Again, I'm biased. I love tempo, so I'll focus on the major advantages of it. There are limitations, of course. I'll leave that and you can read through that and kind of focus on what are some of our limitations, especially thinking about over Canada, right? We do lose some of our spatial information over that region, which can lead to some additional uncertainties in the products and reduced sensitivity to some of the gases in that area. And then, of course, high aerosol loading can be an issue. Wildfire smoke plumes, right? That can lead to additional uncertainties, complicate the trace gas retrievals, and all that. So I'll leave it there and take any questions in the Q&A. Thank you.
We could have all of our speakers come up to the front, and thank you everyone for your nice presentations. But now is the exciting part where we get to ask our questions. If you could wait for the mic to come to you when you have your question, that would be great. So, questions from the audience.
Hi, question for Aaron. We've kind of chatted about this a little bit, but the latency associated with the associated with near real time. Just wondering, is there any potential for reducing that? And if so, how, is there any way, to collaborate or?
That's a tough question. I want to say there is a potential there. It's kind of a limitation on our computational, our cluster at SAO2 and our downlink at tempo data in general. So I don't want to talk too much on that, but I think there is a possibility to reduce that further through collaboration and an effort and more conversation. And that's probably a topic to touch on in the future here for sure. But yeah.
Thanks. We'll go over here to Randall.
Yeah, this question's also about tempo, probably first to Betsy and then possibly Aaron. And the question is whether there is a way to slow down the scan rate of tempo to increase the spatial resolution in the east-west direction. And this came up at the tempo meeting. I got conflicting information. My current understanding is that it's not feasible. But I thought since I have an instrument expert in front of me, I'll ask the question.
Yeah, I heard that question during that meeting and was like mumbling to myself in the background. I'm going to go out on a limb and say there is probably a possibility. So the east-west direction is really dictated by the slit of the instrument. So if you think about a single view, like a single stare, we can't change that, but I don't see why there wouldn't be an ability to scan like sub pixel, right? So if given the tempo people allow you to do this, I think you could be able to scan, less than a single, I guess, step, right? So I'm pretty sure the scan mirror has the ability, like the resolution, to do less than a step. These are pretty incredible mechanisms. So I actually think you could, but the limitations in the east-west, like the pixel itself is defined by the slit of the spectrometer. So there, you can only do so much, but I think we should do it. Do you have a green paper in?
That's the motivation.
Yeah. And I can.
Yeah, I think we can get the conversation rolling by getting the green paper in there and talking to some of the other program managers on that and PIs. And again, it can be done, I'm pretty sure, but will it be done is another question. And
So another thing to think about though is that Tempo is on a platform that's not stabilized like a typical operational satellite would be. And so there's going to be quite a bit of jitter in the measurement itself in terms of geolocation. There is a very nice, sophisticated geolocation that's going to actually rely on the NOAA ABI satellite to do geolocation, but still there's going to be more jitter than you currently see with operational satellites. And it may very well be that now you're talking about moving smaller increments than what that location uncertainty may be. I would bring that up as a possibility.
Yeah, shout out Jim Carr. He's the genius behind the pointing. But yeah, I also think that'd be an interesting experiment, is how far you can push that. And the mirror that does the step stare does do some accommodation for spacecraft movement, but there are uncertainties for every single one of those things.
We're going to actually take a question from online now.
Thank you. From the online audience, Edward Zhang says, what are the sizes and ranges of the drones used for the landfills, and how automated are their paths?
In terms of the sizes, I guess so there are different brands of different companies that doing this drone measurements over the landfills. And not only drones, there's sometimes airplanes, like the actual small airplanes touring. The size of them, I would say, I don't have exact information about the size of the drone, but I guess the information that they're getting out of this, is it proportion to the landfill side? Maybe, definitely, I guess, because in one of my slides, I showed how they're touring around the landfill. Sometimes they're doing this curtain ways, so it could be automated sometimes. We don't have control over the patterns of those. We just get the data out of it. But that could be, but there are some conversations on maybe having the routes predefined, like automated as possible, as much as possible, so that they could pass by some of the sensor locations as often, so that they could validate those measurements. I hope I answered the question.
Great, thank you. A question here from Jesse.
I have one for June and I have one for Amir. In June, in terms of the wildfires, is there any documentation being made as to what is the subsurface geology? Because you're going to have a wildfire, it's going to be burning the shrubs and the trees above. But if 10, 20, 30 feet below, it's iron ore versus granite, which one would, I'll say, generate more heat? Which one might, have a longer burning, so to speak? So is anything being on that end of it?
Yeah, thanks for the question. Certainly, when fires occur, they have the heat release boost up and down. So traditionally, we retrieve what we call fire radial power. That's basically you can use that as a proxy for the heat. The total amount of energy basically in all the radial wavelengths. But I will argue is that the heat if the for the same amount of heat, if the most of the heat is in the flaming phase, the fire is really burning very intensively, and you can see the visible light. Whereas a smoldering fire, but the fire area is bigger, their impact on the subsurface will be very different. You can imagine if it's very flaming, then the soil will be basically, will be, all the water will be gone. You will have the pretty dark side of the things. And actually, we had some papers to look at even from the satellite imagery post fires. You can see the surface is darkening. It's getting darker. And as a matter of fact, the satellite uses that feature to detect how much burn area after the fire. So I think combining the post-fire, like the observation, together with active fire product, like the fire relative power or modified combustion efficiency, you can actually get a little more information about how the subsurface is affected by the fire. I think that's a very hot research area. Certainly need some institute data to deal with it, but I would think it's a very important question, because if the fire, it leads to the soil erosion, right? And if you in the mountains, in the slope, after the fire, if you have a big rainfall event, you will have landslide. So to what degree that fire caused that, and to what degree we can actually use from space to calculate to what degree the soil are eroded and actually a danger zone, high risk for floods. Those things are very important questions.
Because if there's a lot of silicate, for example, and it gets heated, it melts. So instead of having particles, it's like melted glass, so to speak, which means rain comes, boom, it'll wash away even faster. Thinking out of the box,
Let's get back to the early morning questions. Right, we're doing well in the conference. At least we have one idea to pursue.
and then for Amir, we have numerous landfills that are now brownfields and methane. We're setting up our network. We're going to have 5, air quality monitors, and a methane sensor is one of them. But then I see how you show it on your slide. The plane perimeter, the drone perimeter, the possible satellite. But then I'm coming from an activist standpoint, and we're saying, wait a minute. If you're going to do this and you're going to sort of do this, you're leaving out, which is the best way at the beginning. We believe in establishing baselines. So if we're talking about a 50-acre landfill with methane, then to me, no, your plane and drone is not acceptable. And then the satellite shot thing is not acceptable because you don't have a baseline. If you're going to ask me what's the proper way, then the proper would be, okay, if it's 50 acres, then, every mile, every kilometer, put a stationary one there through the whole thing. And now you have a baseline, either at ground level or at 25 feet, however you want to do it. But then that becomes the baseline. So no matter what else you do, you have a baseline, an accurate baseline as to what those emissions are to compare it to with any other means that you use.
Yeah, that's actually a very good point, because in each of the landfills that I showed you only one landfill here. So on each landfill, there are like more than 10 sensors. And on each timestamp, one of the sensors reads the background concentration, because I'm sorry, because there's a possible source in the landfill. We don't know where, right? Because if we knew, everything was solved, then we didn't need to have this discussion. But there's a wind direction and wind speed pattern going on in that landfill. So on each time window that you select, either at 15 minutes or 1 hour or 4 hours, you could select a sensor or a location that gives you a background concentration of methane. Now, this is all concentrations. As I discussed and I insisted in my conversations, concentrations of ground base is really important when you're breathing them. And there's a federal law about the methane thresholds. But the objective of this project is to report the emission rate for a landfill annually, because there are, again, some followed up economical and sustainability objectives with that. Now, of course, for our analysis, for modeling, we would definitely need the background analysis, which is exactly what you just mentioned. We are relying on the ground-based measurements and selecting each of the sensors on a selected time frame to be a background concentration, which is, I know, it could range from 10 to 20, 30 ppm. Now, this is going to be the background. Then based on that, we can say, okay, we have an elevated concentration, for example, across the landfill over there. And then based on the matrix of wind speed, wind direction, temperature, stability, class, and all those, then that's where the conversation starts, and we could model those concentration to an emission rate. But exactly, we know that we need to establish a background concentration so that we don't really mix up things together. Very good point.
Got a question up front here.
For Amir, hey, this is Zach Edelman with LADCO. Are you looking at other pollutants like formaldehyde from landfills?
Very good point, and we should. But again, the scope of this project at the current moment is methane, and that itself is a big problem. So mixing it up with another pollutant might make the scope of it a little going under the trail. But I understand and I agree that, well, there are some audits of formaldehyde into the site that we sometimes use as a tracer correlation with methane. But again, the objective of this study is not. And again, the measurements for formaldehyde, for example, the sensors are very limited. The sensors on the ground base for methane is just beginning to bring, like, so very good point, but definitely along the way.
Great, thank you. Another one from the audience here.
Hi, I'm probably not going to get the vernacular correct on this, but I feel like I've read or seen field studies where there's additional satellite observations when there's like a large sampling campaign to compare ground-based to satellite. But in Utah, we have a lot of issues with retrievals over the highly reflective Great Salt Lake dust area, and also in the Uinta Basin where we get wintertime ozone, but with snow. And is there any way to get extra time to improve retrievals during those conditions or over those places, or is it just kind of like impossible?
So I can comment at least on the PM 2.5 part of it. So with Tempo's complement on NOAA is ABI, the Advanced Baseline Imager. And at NOAA, you can request mesoscale sectors that are 1 minute scans over a particular area. And those are done for research field campaigns. So it's not going to necessarily help with your bright surface issue, because it doesn't matter how often you measure that, you're still going to have bright surface issues, but you can request more frequent scans in that area.
And we have an operation with Tempo that we're doing. I was going to share that slide, but I was talking way too long on my previous slides. But yeah, so we have what we call our Tempo special operations. We can essentially zoom in and do more rapid scans over finer scale areas of our Tempo regard. And we actually did this. Doug Boyer, he's part of TCEQ right here. We did some of our special operations with his campaign. He was doing the Gulf of Mexico during the commissioning phase. And we plan on doing some in the Utah area. There's a field campaign that is being planned out there in this region. And then we have one, which you might relate back to your comment too, with our Canadian partners over the Toronto area and doing some more rapid scans for their field operation in Canada. So that will really focus on that snow covered issue you're talking about now. That will happen this upcoming winter, actually.
So we'll just have time for one more question, and we'll stick with Aaron, and it's from online, and I think it'll be of interest to multiple people.
For Aaron, is there an appropriate time frame for the ArcGIS tool development for Tempo data?
We have our ASDC folks here in the crowd. Maybe they've been working on that too. We kind of have our own ArcGIS operation we have been building at UH and NASA Marshall, but I know they've been doing a lot of work at the ASDC and on that too. So if they want to make a comment on that, feel free to.
Thank you, Aaron. Well, we are expecting level 1 data in end of January, early February, and level 2, level 3, we're talking about March, early April. So we are going to have a window of 3 to 6 months to have this available after receiving the final data after commissioning. Thank you.
In terms of the ArcGIS, so I know you've been building those tools. Do you plan on having that kind of up and going in the April 2024 release then for Tempo at the DAC, or for your ArcGIS tools you're building? I was wondering the question relating to GIS. I know you've been building, you're having Worldview there available. We know will be in Worldview, but do you think that the ArcGIS capabilities will be built already by the April 2024 time frame?
So Worldview is in progress now. We are working in the UAT environment. UAT is standing for user accepting testing environment, to make sure everything is tested properly. And regarding EGIS, or Earth Data Geographic Information System, is going to be in the cloud, and this is also in progress. We are expecting this to be ready after receiving the level 2 and level 3 data by March. Thank you.
One additional comment. I think it's great that NASA will develop these ArcGIS GeoJSON files instead of NetCF, so that the user community that's already doing ArcGIS can easily bring the data into their current systems.